which algebraic geometers might call correspondence, is just a diagram in any category that looks like this. So it looks like a little bridge. So we'll be looking at spans of groupoids. So all these three things here are groupoids, and then these arrows here will be functors. And so spans generalize functors, because if I have a functor from x to y, I can turn it into a span by just putting the identity here.
Kind of span like that can be translated to a distributor.
Yes, that's right. Yeah, I'm sort of thinking more of in the span picture than the distributor picture here. But the good thing is that you can also turn it around and get a span going backwards the other way. So spans are more like a dagger category, dagger bicategory. You can turn things around. So if you have S, the groupoid of finite sets, there'll be a span called the annihilation operator, and the turning around version called the creation operator. So I'm reading all these diagrams from right to left to stick with sort of traditional function notation. So here we start out with a finite set, we don't do anything, then we put in an extra element, that's creation. But here, it's going backwards, and so there's one less element here than there is here. And if I start with a finite set, there are many possible choices of which element we put in. So this is, if you try to read this backwards, there's many possible choices of which element we take out from here to get one here. So that lets us talk about this choice. So you can compose spans. You compose spans using pullback, but for groupoids you need to use what's called a weak pullback, because groupoids live in a 2 category. So if I have a span from x to y and a span from y to z, I can close them to get a new span, which I'll call S followed by T, TS. And the idea is this will be a new groupoid. And an object here will be an object of T and an object of S, and an isomorphism between their images in Y. So that isomorphism will be part of the data of an object. So if you're doing an ordinary pullback, we would just write an equal sign here. But because groupoids, you don't want to say things are equal, you want to say they're isomorphic, we put an isomorphism there. So that lets us compose the annihilation and creation spans. And you can prove that well, I haven't said much about how we add spans, but it turns out that this Heisenberg relation will hold up to equivalence of spans. But let me say what this means exactly. So first of all, for any groupoid, there's an identity span. We'll just use identity arrows. So that's what 1 means in this previous equation. There was a 1 there. That would be an identity span. And then there's also addition. We can add 2 spans just by taking the coproduct or disjoint union of the 2 groupoids up on top. And there's an obvious map from that to here and here using these 2 spans. So we have a kind of basic linear algebra of spans of groupoids. The idea here is I'm trying to use spans of groupoids as a substitute for operators between vector spaces. And I'm only telling you a little bit about this so far, but I'm telling you that you can add them, like you can add linear operators. There's also an identity. And then there are such a thing as maps of spans. So if I have a span and another span from x to y, a map of spans is a functor from here from S to S prime that make these triangles commute up to some chosen natural isomorphisms. If F is an equivalence of groupoids, we call this an equivalence of spans. And so that means they're sort of the same, roughly. And we should only expect various equations to hold up to equivalence. I mean, we won't really get equations anymore. We'll get these equivalences between spans. So you can prove, although I won't do it here, that there really is an equivalence of spans between A dagger A plus 1 and A dagger. And the proof is a good exercise to see if you understood all the concepts, and it's a little bit tiring at first to do, but if you finally get to the interesting part of the proof, you discover that the key reason why it works is just this simple idea that there's one more way to put something in a pot and then put a bean in the pot and then take a bean out than the other way around. So here, this is the process of putting something in the set and then taking one out, and there's sort of two choices. Either the bean you took out is exactly the one you put in, there's one way that can happen, or it's another one. If it's another one, you could have taken that other one out and then put your bean in. So you can work it out. So James Dolan and I noticed this in 2000. We noticed that we could categorify the Heisenberg algebra by using spans of groupoids as a substitute for operators, and then we got this isomorphism here as a substitute for the relation in the Heisenberg algebra. Then once you know how to do that, you can do lots of other things people like to do in quantum mechanics. People like to describe interactions of particles in quantum mechanics using things called Feynman diagrams, and it turns out all of that, not all of it, but a large part of that can be developed using spans of groupoids, and certain kinds of things actually become clearer. I mean, so for one thing, you're completely avoiding any use of the complex numbers or Hilbert spaces, so it's sort of logically simpler. But second of all, there's some kind of combinatorial questions about Feynman diagrams that can be really understood nicely this way. We're getting straight to the combinatorics. Of course, physicists want to have the complex numbers, not because they're just used to complex numbers, but because they seem to be required for full-fledged physics. And my student Geoffrey Morton showed how to put the complex numbers in there if you want. But then later in 2012, Morton and Vickery showed that this isomorphism here actually obeys some non-trivial equations, which are precisely the relations in Kovanoff's Heisenberg algebra. So I think of this as a step forward because I understand this better than what Kovanoff originally did. Although now I can go and look at what Kovanoff did and I can understand it because I know this easier way.